So, hello everyone, my name is Lucia from Team Germany, and today I present you the problem Origami Launcher. So at first the task. The task was to build an origami cannon that can vertically launch a ping-pong ball, and the restriction was that we should only use a single uncut sheet of A4 paper. And we also should maximize the parameters such that we achieve maximum height. And it was also given that we have this origami called Miura-ori, which we can use for that. So basically the task is to find out how much energy can I store in a paper pattern, for example in the origami pattern. So this is what we did on the theory side. So we modeled how much energy can I store in my folding pattern. Then we compared it to measurements, so we measured the energy. From that, we estimated the takeoff velocity of the ping-pong ball and modeled a trajectory for the ping-pong ball, and thereby could gain a model for the height, and then measure the height and compare that. So, what's the most simple paper construction that comes automatically to mind? It's just a simple Hookean spring, and we did that. We folded a A4 paper lengthwise and then added creases. And the model is very simple, it's just a spring. Then let's move on to the Miura-ori fold. Miura-ori, as you can see here or here, is mechanical metamaterial. It's composed of periodic repetitions of those unit cells. And the unit cells can be described by three parameters. We have one angle here, and two lengths. So here L1, L2, and the angle alpha. And the state, that means how much the pattern is compressed or stretched, can be described only by the one angle theta. Here is also the angle beta, but beta is when you stretch it or compress it is dependent on theta. So that will be our parameter for the state. So coming to the model we built, you can write down, we modeled the Miura origami as a simple toroidal spring for each single paper crease. So we modeled the spring for a paper crease, and then we summed up, as you can see here. So a toroidal spring basically means that the force is proportional to the difference in the angle. And so you get for the energy the angle squared. And then, as you can see here, you can sum up all the energy for all the creases in the pattern. And then you can change variables so that you don't have anymore there theta and beta, but that you have the nice variable h, which is the total height of the structure. So here is the energy we derived, and now let's take a look. What would an ideal pattern look like? How can we maximize the energy depending on the height? So as you can quickly see, we have L1 and L2, and E of h is proportional to 1 over L1 and 1 over L2, so we can choose those two small, and then we can maximize the energy, and the same goes for alpha. And so for our experiment, for practical reasons, we selected those four patterns. So the model I just talked about requires one parameter from experiment, namely D. And so we measured D for a single paper crease with the setup you can see here. Our setup was such that we could only measure the force in the z direction. So here we have the force which is protected to the z direction, and then we simply fitted that function to our values, and we get to about 1.4 10 to the minus 2 for the constant d. So now that we determined d, we can plug that into our model and calculate for the patterns we selected what E of h would be like. And parallel to that, we made measurements. So we used the same setup as before, as you can see here. And then calculated the energy by a numerical integration for the 4 patterns we used. And as you can see, the model and the experiment agrees with an error range. And so, yeah. So we also did a similar thing for the zigzag fold. There we had two patterns, one with 7 creases, one with 9 creases, and we get an energy that is in the same range as the one for the Miura-oris. And we could also calculate with the fit you can see here. We could also calculate the spring constant. So now. What I only did is to estimate the energy stored in the pattern, but we actually want to model a ping-pong ball that jumps. So we need to estimate the takeoff velocity. And for the takeoff velocity, we need to think about how much of the energy that is stored in the paper really is transferred to the ping-pong ball. And we took into account 2 energy losses, one due to expansion. So as you can see here, when the spring jumps, it expands, and therefore the potential energy of the paper rises. It expands, and the other thing is that it jumps. And so we took those two losses into account, and then we calculated from that the takeoff velocities for our 6 patterns, as you can see here. Now we have the takeoff velocity. We need to go one step further. Now we need to calculate the maximum jumping height. And this we do by modeling the trajectory. So we assume that the ping-pong ball flies through the air and experiences Newtonian air resistance, so that the friction is proportional to v squared, as you can see. Here we solved the differential equation and then maximized the height. And for that we get here heights from 50 centimeters to 3 meters. So now this is our final theoretical result, and now we have to compare it to our experiments. Therefore we used setup you can see here. We have some metal bars that restrict the movement of the ping-pong ball to the Z direction. So that because only we try to launch the ping-pong ball vertically. And then we compress the pattern and so that it's only 2 centimeters high, and then we release it. We filmed the setup and then made a trajectory analysis with the program Viana to determine the maximum height. Yeah, and here you can see our results. So there's a huge deviation from the maximum height we reach in the experiment to the theoretical height, but nevertheless we could reproduce for the Miura-ori the qualitative behavior we expected. So for the smallest angle as we expected, we get in the experiment the biggest height and vice versa. So what could be the reasons that there's such huge deviations? So there could be some additional losses, or there are some additional losses. One of them is the rotation of the ping-pong ball. So it's unavoidable that because our setup is not perfect, that the ping-pong ball starts rotating when you launch it. And then there's also friction from the metal bars. So when you don't really manage to launch the ping-pong ball vertically because it's not perfect. Then in addition to that, mechanical stability of the pattern you can see here, because especially for small angles, the Miura-ori patterns tend to have a very narrow baseline, so they tend to buckle to left and right. And this also leads to what you can see here, that it's hard to compress the paper uniformly. And also the paper creases tend to wear out after a certain time after the first measurements. And so to sum up, what is the best folding pattern? The best folding pattern definitely is the zigzag folding. We reach the maximum height of 0.5 meter, theoretically it could be up to 3 meters. And for the Miura-ori, the more paper is creased, the more energy can be stored in the total pattern. Yeah. And our first mathematical model agreed with the experiment, but for the height we didn't reach the maximum height we expected, but the qualitative behavior was confirmed. So, thank you.
Thank you very much.
Yes, so good afternoon, ladies and gentlemen. My name is Irina. I'm from Team Ukraine, and I'm glad to be an opponent of the problem number 4, the origami launcher. Thank you very much, dear reporter, for the work done. Let's analyze it. Firstly, your task was to construct the origami launcher to find the dependence of the height of the ball on parameters of the system, and to do the optimization of your construction to find the best construction for the maximal height. So your report was organized with a theoretical part and with the experimental part. We will start from the qualitative explanation of the phenomenon. Firstly, you considered the simple zigzag folding and you described the parameters of the Miura-ori that distinguished of the simple zigzag folding. This is very strong point of your report, because the parameterization of the Miura-ori is very important to the variation of parameters, but still you don't describe the impact of the construction, because as we know there are a lot of any constructions besides the Miura-ori, and it was the task of the problem, and you don't vary the other constructions, so I think it is a strong point to improve in your report. So we move to the theoretical part. Firstly, you modeled a single paper bend. You wrote down the dynamical equation for the single bend. However, I would like to point out that the dissipations in the paper weren't considered, and I think it is very important, because as we know, the elastic properties of the paper are strongly non-linear. That's why I think that the model of the string is not applicable here. However, the strong point of the reporter is to measure the force experimentally, and it is a way to compensate this weakness of the theory. Then you found the way to maximize the energy described. This is the task of the problem. You estimated the takeoff velocity and Newton air resistance. Yes, you considered it. However, I think this energy dissipations are relatively small in comparison with the dissipations in the paper, and you haven't considered it. And finally, you found the best folding paper for the zigzag origami and for the Miura-ori origami. It is a very strong point of the report. It is the answer to the question of the problem. However, what is the physical basis behind the best construction? Why we cannot do the further optimization, and why this construction is the best? I think it is the main question for the discussion, and it is the main question in the problem. And finally, the experimental part. It was a great experimental part, a large experimental basis. Firstly, you measured the energy of the single bend, then you measured the force depending on the angle. The text at the end, it is very well, because when you have a non-linear spring with dissipation, the experimental measurement, this is the only way to study the system. You studied the dependence for the zigzag Miura, for the zigzag origami, for the different number of creases. It is very well. You constructed the setup for the vertical launch. However, I would like to stress that your setup can lead to the dissipations, as you notice in your report, and I think it's important for the maximal height of launching. And finally, you studied the height of the origami structure, and you done the variation of parameters of Miura-ori. It's very well. You varied the angle, and you obtained many curves for it. However, the experimental technique with Miura-ori was a bit unclear. How do you ensure the vertical launch? How do you vary the parameters? And why your result for the maximal height? It is really the maximal height possible? What is the optimum in the theory and in your experiment? I would like to discuss this question during the polemics, and finally I would like to present you a list of discussion points to clarify the physics besides the problem, to find the ways to improve the solution, and also maybe to discuss what construction is really the best, and what is really the answer on the question of the problem. Thank you very much for your attention.
Thank you very much. Now we have 5 minutes of discussion with our reporter.
So the first question that I would like to discuss is the different deformations of the paper, bend, stretch, shift, etc. As you know, a Miura consists of the deformation of bending, and in the zigzag we have many layers. That's why there is a deformation of stretching, and physics and rigidity of these deformations are completely different. What do you think about it?
I think that the bending actually doesn't have much impact on the Miura-ori, because the Miura-ori is a metamaterial, so the properties depend mainly on the folding pattern and not on the material, the paper. And therefore we assumed that the paper pieces which are not creased are rigid. And I think this is a valid assumption here, because we also saw that in my report, the first model, E of H, we could confirm our model by experiment, so I think there's no problem here.
Okay, it's clear, but I would like to stress out that when you have a zigzag with many layers, the deformation in these layers maybe it's the deformation of stretch, and the rigidity of this deformation is bigger than for the simple bending with a single layer of paper, and it may increase the energy accumulated.
We only had 3 layers of bending, so I think,
okay.
yeah, so because we folded the paper 3 times.
Do you agree
for the
that
zigzag fold, we also only measured the total energy stored in the total construction and not for the single crease. So I think because there we don't even have a model for the single creases, so I think that's just not important here, because it was
okay,
not
thank
included.
you. Your point is clear. The next question is the impact of the hysteresis in the paper and the dissipations in the paper bend. How maybe could you improve the theory, including the dissipations and the hysteresis in the paper layers?
We could, for example, measure. Do you mean that the paper wears out after some time? So we could, for example, make a measurement and then measure how the initial length of the paper changed after the measurement.
Okay, and how many times in your experiments do you use the same construction with the same sheet of paper?
I only used it for the. I think 3 times for the jumping height, and then I used a new one.
And then you change the origami, yes?
No, then I repeated the same process with multiple origamis of the same time.
Okay, and what do you think when we do the origami? Maybe the human factor may influence the bending properties?
I don't think so, because the one property of the Miura-ori is that it kind of shifts itself in the shape. So when you start folding it, it automatically folds in the same shape. So if you crease one of the creases, if it's for example, too far to the left, and the next one is too far to the right, it corrects itself.
Okay, and
so
now what is the influence of the initial compression? It may seem that the compression will increase the height of the ball. However, we say that there is.
I always took 2 centimeters as compression for all springs.
Okay, and what is the optimal compression? Maybe this way we
could go farther, maybe, and increase the height. But the problem is that at some point our model breaks down and it gets very hard to describe it. So I had to take, and also maybe some models, some Miura-oris, I can compress farther than others. So I just have to find a common height for all, and so I took 2 centimeters.
Maybe you have done some optimization in the experiment. You have noticed some the optimal compression, yeah?
I always took 2 centimeters because.
Why 2 centimeters?
Because this is the farthest the farthest length I could get down for all the constructions, because I wanted to compare the constructions, and therefore I have to compress them all to the same length.
Thank you very much. And the last and the most important question, how to improve the construction? Maybe if we use not a flat Miura-ori, but maybe cylindrical or something more complicated, we will obtain this result?
You mean that you could also bend the Miura-ori out of plane? I don't think that this is appropriate for this problem, because out of plane bending really you can't. In our model, what only matters is how much you compress the single creases.
Yes, okay, but my question is about the construction like Miura-ori, but not Miura-ori, because the question is about...
I only took account Miura-ori, but Miura-ori itself can be very different. We had those 3 parameters, and so we varied the 3 parameters and concentrated on that.
Thank you very much. It's the time for the review questions. Yes.
2 minutes of question from the reviewer.
So first, we saw the reporter presenting the problem, and first we had a description of Miura-ori origami and a thorough explanation of what it was and how the parameters work. And then we went into
You should listen to something. The screen. What? Screen is virtual.
Okay, just to speak, I'll scroll.
Okay, so could you go down? First we went into how energy can be stored, and then we saw Miura-ori origami and how energy was stored in there. First we saw the simplest folding pattern, the zigzag pattern, and then we went into the description and model for Miura-ori origami. And they described their springs as torsional spring model, and then we saw a comparison of the model with that data, and they measured the initial velocity of the pink ball and made a theoretical relation between energy and height by assuming it was Newton drag. Though they did not actually measure the maximum height. And then they had a discussion about additional losses as their results did not match with the theory. And then in the conclusion we saw that the zigzag folding was the optimal folding. However, they did not clearly present the optimal parameters than of their springs. Then we went into okay, so the evaluation of the discussion was the deformations was mainly in the bend, twist, and stretch, etc. And then it was a lot about energy dissipation in the springs. And the human factor was, is this?
Okay.
Thank you very much. Time is over. Now you have 4 minutes of discussion between a reporter and an opponent, moderated by the reviewer.
Okay, first I would like to ask about, can I see the questions?
Points to discuss?
Yes, there are. Okay, so it was a lot about energy dissipation in the paper. So then the energy lost by plastic deformation, as seen in wear and other things. Could you discuss that for the springs?
So, what do you actually mean by energy loss by plastic deformation? Our model just suggests that we have a toroidal spring, so we don't consider another energy loss. We didn't consider that the paper result for our model.
Okay.
So this is what I discussed. And
You assume
Yeah.
the Hooke's law was a linear relationship between the
Yes,
compression.
that was for the zigzag fold, yeah. And we also saw, I didn't show you that, I only showed you the linear effect, but we had a deviation from the linear behavior up, below a certain height. And we took that into consideration when calculating the energy, because we integrated numerically and then you can do that. So,
Do you have anything?
Yes, I would like to add something about the plastic deformation. Indeed, I think that the plastic deformations are very important in the paper, because the zero position from the for the paper, it is not the plain paper, because we have some residual deformations that results in some angles that rest after the work of the origami, and this is the angle due to plastical deformations. And I think that the Hooke's law is applicable for only a small range of small differential.
yeah, we didn't apply the Hooke's law here. We did apply the toroidal spring model there.
Okay, thank you.
So, yeah. I also I have a point. You said that I didn't specify the opto parameters, but I think I did that. I said it's better.
It was first when she asked you after the presentation.
Okay, but I
perhaps you presented it, but not clearly, as I stated.
But could you please repeat the important the final parameters for the Miura?
Well,
for
could we go to
So
another?
the best parameters are you have to choose the length L1 and L2 very small, and also the angle alpha small.
Can we go into that? The length L1 and L2. If it was a certain energy from each fold, then why did it not go further? Why didn't it produce more? Is there a maximum
That's
number
not.
of folds?
The problem is if you make L1, L2, and alpha smaller than I did in my experiments, then it's really hard to do all the folding. So you would need a machine to do that. So I did this thing I could do by. And also another point is that the smaller alpha gets, the broader the whole structure gets. So you have a narrow base area, as I just said, and the structure also gets longer. And then you have buckling, and the structure isn't at all ideal for the launching of the ping-pong ball. So I don't think it does make much sense to go below that.
Do you have an estimation of the maximum number of folds?
Well, I said, as I wrote there, I can calculate the maximum number of folds in my sheet.
Okay, so why is the cause that you cannot even more increase the height of the ball? What is the physical cause of it?
Well, the physical cause it's limited because I have a ball, and I have to launch it from this very narrow base area, so I can't do
So
alpha
this
much
is
smaller,
stability
and I also
angle.
can't make L1 and L2 much smaller, because then I don't have anywhere to put the ball.
Okay, and
So these are
The audience
experiments.
may join the discussion if they want.
Okay, could I present a new thing? Okay, so elastic versus plastic folds. Yes, I think you may join in if you want to join in the discussion, or I'll present a new point to discuss. So, okay, so we saw the zigzag folds. They were mainly like this is a pretty bad one. It was sharp folds. However, if we make
We did always do sharp folds.
yeah,
So
saw
I
it.
took a
So
ruler
could
and
you
always.
discuss the difference between the sharp fold?
So
and
in
the
this
smooth
fold, you don't destroy so much of the paper, and therefore you also have to take into consideration how much the paper bends and all that stuff we discussed before. But I didn't want to do that. I wanted to assume, as I also assumed for the Miura-ori, that it's rigid and that the paper doesn't wear out so fast. So I just have to bend it once very heavily with a ruler, and then the bending
Okay, I think
hardly
we get it.
changes.
Can we get
Yes, thank you. One more question about the experimental stuff. And sorry, have you tried to rotate your paper on 90 degrees? Because we know that a list of the paper is not isotropic material, and it consists of fiber, and these fibers are originated along one side. So we would try to rotate
Yeah,
it on 90
that's
degrees.
a very good point, but I didn't consider it. But thank you. I think that would be a really
And
good
could I
point.
But-
please,
but-
say
but
something
if you
about your
did-
previous question, yes?
Could I would like to say?
Your previous question with the two different cases, I think it is really the plastic deformations that you proposed us to discuss, because if we consider the microstructure of the paper, there is many layers, and when we bend the paper, the layers separate from each other, and it results in the plastic deformations and the residual angle. So this is the difference between these two zigzag foldings.
Could we get the comments?
Yes, so to the opponent, you described the negative aspects and the properties of the setup weren't described really precisely, and that you would have, they would think that different parameters are more important. Can you point out what parameters and what properties you mean with this?
In my opponent's speech, I told about the experimental setup for Miura-ori, because we saw clearly the video with the experimental setup for the zigzag folding,
So
but not.
You mean it was the same way? So we also took the spars and we also put the Miura-ori in, and I also discussed that you have the problem that you can't compress the paper uniformly if you just press down the ping-pong ball.
So during the discussion, it was not clear. Thank you very much for
Please,
the
can you just
clarification.
describe your parameters, your properties that
So-
are important for you?
I think that the parameters
Can you
appointed in the report, such as the angle and the length of the sides, it is a very good description of the Miura-ori, and I completely agree with this parameterization of the Miura-origami.
I'd like to ask the opponent, you're mentioning a lot about the plasticity and the folding. However, I'd like to ask you about the stored potential energy. If we can take a metal rod and store a lot of energy, however, if we put a ping pong ball, it won't fly anywhere.
Okay.
The question is, it's more about the acceleration distribution over time. Do you have any comments on how an optimal
Yes.
acceleration distribution would look like?
In the report, we heard about the compression of the same compression in all the experiments. However, I think the physics of different compressions is not the same, because for the very strong compression we have another type of deformation. It is the deformation of all sides compression, and the theoretical basis behind this compression is different from the theory for the gradient. It's not the gradient, it's some elastic medium, so maybe it is out of frame of the problem is that the compression is too large.
Thank you. Another there?
We saw clearly we had limits because of the setup, and we also criticized this. So the question to the opponent, what are your ideas for a setup, or what would you?
I think that if in the experimental setup we are interested in the dissipations, we understand that if we remove the rigid rows near the construction for the vertical launch, we will obtain not vertical launch of the origami. However, we can collect the statistic and to choose the best ones, the vertical launches, and to do our experimental plots with these 1 point.
Thank you very much. 1 minute for concluding remarks.
So I thank you both for this very interesting and enlightening discussion. I think you brought some very new aspects to the problem. So you talked about how the bending of the paper is important. I think that, but I also think that my approach is valid, that you can model the origami as rigid. I think that there are two different approaches, and I think it's the best if you combine those two. And I think there were also some good ideas how to improve the experimental setup in the process. So thank you for the nice discussion.
Thank you.
Now, if the jury may have some questions, curiosities, you can ask the three of them. Not necessarily, I didn't mention this, but you can also ask them about their own work. Well, of course, you cannot grade them based on their answers. Okay?
I have a very general question. You mentioned squeeze paper is a metal material. What do you mean by that? What is metal material in this case?
That just means that properties of the paper mainly depend on the folding pattern and not on the material, so not that it's paper. And that is a property of the Miura-ori and one of the things why it's so interesting in many different fields. It has many different applications.
I got a question to report too. On your theoretical results, there is a distribution of the maximum height,
Yes.
and I don't remember which one was, but was about 3 meters the maximum height.
Yes.
But your experimental was different.
Yes.
It's not the same origami that
Oh, yeah,
was the
it
maximum.
were
Why?
exactly the same origami patterns. I compared the origami patterns I folded with the theoretical predictions. So
Oh, yes, but the maximum in your theoretical results was not the same with the experimental
it was the
results.
same. It was we had the highest for the Miura-ori.
Can you show this slide?
Yes, maybe. So. Sorry. So you can see here that we had a prediction of about 3 meters for the smallest length and smallest angle as predicted by the theory, and we also had the highest height in the measurement. So I think that we can say that our predictions were at least confirmed qualitatively.
Yeah, but wasn't zigzag the...
Yeah, but that are two different models. Zigzag is another model than this one.
Okay.
So, and I also said in the end that the zigzag is, for our purposes, the best. And I think the case, why this is the case, is just that the base area is much more suited for the ping-pong ball than for the Miura-ori. So maybe you would have to think of some nice idea how to construct a launching pad for Miura-ori pattern.
Okay,
Thank you.
Okay, so just to continue this discussion, so what exactly is now this mechanism that explains this order of magnitude difference? Is it the friction between the supporting structure, or is it the...
Yeah, I had a lot of points, and I think they all contribute to that. I think one of the most important things is the mechanical instability, because we didn't manage to really to stabilize the paper, the Miura-ori, without adding additional friction. Because if you move the metal bars closer together, then there's friction and it can't expand freely, and then you don't get the jumping height. So this is a challenge, and I think that's the most important point. And related to that, if you get buckling here from the paper, then the ball doesn't launch exactly vertically, and then you get friction from the metal bars. Yeah, so I think there are a lot of points and a lot of work here to be improved on that.
Well, I have a question, more my curiosity. So this is the work where the quality of the work can be described by a single number, which is the height to which the ball reaches. How high did you guys get?
1.5 meters.
1.5?
Yes.
You?
The maximal height in what case? For the Miura-ori, for the zigzag, for any origami, for what deformation?
As much as you want to tell us.
It is something about several meters, 1 or 2 meters, and it is the case when we use the deformation of stretching, because indeed the deformation of bending doesn't allow us to accumulate a lot of energy. But in the case